Hi children, welcome to Form 7. Under Form 7 Chemistry, today I am discussing topic 11, Kinetics. Textbook page number 3231. Objectives of the lesson. There are 11 objectives in this lesson. Some of them are understanding the terms related with kinetics. It means what is rate of reaction, what is half-life of the reaction, what is the order of the reaction, what is the overall order of the reaction, and what are the methods or experimental techniques to obtain the rate of reaction, and how to investigate the rate of reaction, and how to deduce the order of the reaction, 0th order, first order or second order. In this lesson, we are talking about the rate determining step and how to deduce a reaction mechanism and what is SN1 and SN2 mechanisms, and how to find activation energy using Arrhenius Equation. And finally, we will learn the use of heterogeneous catalyst for industrial reactions. Now we will start our lesson. Rate of reaction. What is rate of reaction? Rate of reaction means how fast reactants are converted into products. So we can say rate of reaction equal amount of reactants used divided by time, or we can say rate of reaction equal amount of product formed divided by time. Here I am giving an equation. A and B react and form C. How fast C forms? By used up A and B reactants. There are some factors which can affect the rate of reaction. Some of them are the surface area of the reactants, the concentration of the reactants, the temperature at which the reaction is carried out, the presence of a catalyst. If it is a photochemical reaction, light is also an important factor. Now we will discuss experimental methods for measuring rate of reaction. The rate of reaction can be determined by following some aspect of the materials which changes as the reaction proceeds. If we think we need to find out the effect of concentration, so what we are doing, we are changing the concentration of the reactants. So very important to keep other factors such as temperature constant during the process. First method, mass changes. Mass changes that take place during a reaction. It means before the reaction and after the reaction. Can be followed by placing the reaction vessel on an electronic balance and reading the mass at specific intervals. Second method, volume changes. When a gas is given off in a reaction, if we consider magnesium react with dilute HCl, what are the products? Magnesium chloride and H2 gas. So there is a gas evolving. So those reactions, we can find out the rate of reaction by measuring the volume of gas collected at various time intervals. To do this type of reactions, we need a gas syringe or gas vessel. Now we will discuss pressure changes. One useful way of following the reactions of gases, if a pressure change take place, to connect the reaction flask to a pressure meter and measuring the pressure at given intervals. Next experimental method is titration. There are various types of titrations: acid and base titration, redox titration, iodometric titration. If you consider iodometric titration, we have to do the titration to detect or to find out the rate of reaction. How we are doing? First, we have to pipette the samples of the reaction mixture would be removed from the reaction vessel, placed in a flask and the reaction quenched. It can then be titrated to find out the concentration of the reaction mixture at a particular time. Then we can find out the rate of reaction. Polarimetry is another method to find out rate of reaction. This method is suitable for reactions involving optically active substances. Another method, measuring conductivity. This method is suitable for reactions producing or consuming ions, cations or anions. Another method, colorimetric measurement. If a reactant or product is colored, it gives color. The reaction can be followed by using a colorimeter. This measures changes in color intensity. Here I am giving a diagram of colorimeter. The total order of the reaction for this chemical reaction can be found as the sum of the separate order M and order N. So we can say the total order equal simple M plus simple N. In your A2 level, we will discuss order of the reaction from zeroth order to second order. Now we will discuss zeroth order reaction. Zeroth order reaction means the concentration of any of the reactant has no impact on the rate of reaction. So it means you can see this graph when the concentration of the reactants are changed, the rate of reaction is constant. It is not changed. It is shown as a horizontal line. So we can say the rate equation, rate equal simple K. Simple K means rate constant. Here the intercept of this graph is simple K, rate constant. Now we will discuss first order reaction. It means when we are changing the concentration of the reactant, what happened? The rate of the reaction is changing. When we increasing the concentration of the reactant, the rate of reaction also increasing. Actually, the concentration of the reactant and rate of reaction are directly proportional. When we doubling the concentration, doubles the rate of reaction. So we can give the rate equation, rate equal K A concentration. Here we'll discuss second order reaction. The rate is proportional to the concentration squared. It means if we doubles the concentration, the rate of reaction will be increased the rate by 4. We can give the rate equation, rate equal K A concentration squared. Rate constant. The rate constant for a reaction is constant when the reaction temperature is constant. It can be found by rearranging the rate equation for that reaction. If you consider zeroth order reaction, the units of rate constant mole per liter per second, or we can say mole per cubic decimeter per second. If it is first order reaction, the units of rate constant equals to per second. If it is a second order reaction, the units of rate constant equals to per mole liter per second, or we can say per mole cubic decimeter per second. Finding order of reaction from initial rates. There are three methods of measuring orders. First method, the initial rate method. Second method, use of rate concentration graph. Third method, the use of concentration time graph plus half-life. First, we will discuss the initial rate method. The initial rate means the rate at the start of an experiment, when the concentrations are easy to measure since they have not had time to change. It is often not easy to measure the initial rate, but if it is known, the order of reaction is fairly easy to find. If possible, try to compare experiments in which only one concentration changes. Next method, rate concentration graphs. If the rate can be measured at different concentrations, we can use this rate concentration graph method. If you consider if it is a zeroth order reaction, there is only a horizontal line. If it is a first order reaction, the rate of reaction is increasing linearly. If it is a second order reaction, the rate of reaction is increasing exponentially. Third method, concentration time graphs and half-life. The half-life of a reactant which is not in excess is the time taken for its concentration to decrease to half its initial value. If we consider there are 100 substances or 100 moles at the beginning, the time which the substances are becoming to 50 is called as half-life. Or we can say the concentration is decreasing to half from its initial value. For a first order reaction, this half-life is always constant. Now look at this graph. Here it takes 10 minutes for the percentage of reactant remaining to fall from 100 to 50, and then another 10 minutes is consuming to from 50 to 25. Another 10 minutes is consuming to 25 to 12.5. If it is a second order reaction, there is a successive half-lives double. Now we will talk about reaction mechanisms. Many reactions take place in a single step. Some of the reactions take place in a number of steps, or we can say it multi-step reactions. So what is this reaction mechanism? The way in which atoms, ions or molecules interact stage by stage is known as reaction mechanism. In a reaction which has several stages, or we can say the multi-step reactions, the different stages will proceed at different rate, maybe fast or maybe slow. The slowest step which will determine how long the reaction takes place. So this step we can say rate determining step. This rate determining step controls how long the reaction takes place. Then the substances in this step will appear in the rate equation. Now we will consider the reaction between propanone and bromine. We will consider this reaction is a first order reaction. We can say the rate equation equal K means rate constant, concentration of propanone power A, concentration of bromine power 0. So it means the rate is proportional to the concentration of propanone but independent of the concentration of bromine. So it means this reaction takes place in a number of stages but rate determining step is involved only propanone. If you consider mechanisms and kinetic data, chemical reactions occur when molecules collide. At a given temperature, a constant proportion of collisions is likely to be successful. If we consider molecules A and B are in the same vessel or same reaction mixture, the number of collisions between A molecules and B molecules depend on their concentrations. So we can say number of A and B collisions is directly proportional to concentration A and concentration B. Now we will talk about SN1 and SN2 reaction mechanisms. SN1 reaction means unimolecular nucleophilic substitution. SN2 means bimolecular nucleophilic substitution. Here I am using an example, hydrolysis of halogenoalkanes. First we will consider SN1. So here only halogenoalkane is used to react in the rate determining step. So what happened? If you consider halogenoalkane, here it should be tertiary halogenoalkane. First carbon and halogen atom. The covalent bond should be broken. And then OH minus should be attached. But if you consider SN2 mechanism, both steps happen in a single step. So what happened? First OH minus is coming to carbon delta plus, and then at the same time bromine also, or we can say it's C and Br bond also breaking. Here I am giving a comparison between SN1 and SN2 reaction mechanisms. I will discuss major differences between SN2 and SN1 here. If you consider SN2 reaction mechanism, it is a one-step reaction. For this one step, two molecules are involved. That's why we can say it bimolecular reaction. And always this product formation takes place by transition state. No carbocation rearrangement. As well as this reaction is favored by polar aprotic solvents. Normally, this SN2 reaction is given by methyl halides, or we can say primary halogenoalkanes. Now we will discuss SN1 reaction mechanism. It is two-step mechanism as well as unimolecular. Only one molecule is involved. Product formation takes place by carbocation intermediate. Carbocation rearrangement can be seen. Reaction is favored by polar protic solvents. And normally this SN1 reaction mechanism is given mainly by tertiary alkyl halides. So we can say tertiary halogenoalkanes. Now we will discuss the transition state theory. So here I am discussing what is transition state theory. When molecules collide and react, they move through a state of instability or high potential energy. We can say it transition state, or we can say it activated complex. The energy required to attain this transition state is called as activation energy. Here I am giving this activation energy as EA. Now I will discuss effect of temperature on rate of reaction. As we know, when we increase the temperature, the rate of reaction is also increasing. If we increase the temperature by 10 Celsius, it can double the rate of reaction. Here I am giving the Boltzmann distribution of energy graph. Here you can see T2 temperature is higher than T1. So what happened? At higher temperature, a greater proportion of molecules exceed activation energy. Therefore, rate of reaction increases. Arrhenius equation. It is an important equation linking activation energy, temperature and rate of reaction. The Arrhenius equation is K equal A E exponential minus EA over RT. Here K is the rate constant. EA is the activation energy. R is the gas constant. T temperature in Kelvin. A is the Arrhenius constant. This is connected with the number of collisions and collision orientation. When we consider Arrhenius equation, we can see the relationship. The activation energy increases, the rate constant will decrease, as well as temperature increases, the rate constant also increases. Here I am giving a table how the rate constant might change with activation energy. Earlier we said activation energy increases, rate constant will decrease. Here activation energy 40 kilojoules per mole. At that time rate constant 74,800. When activation energy is 70 kilojoule per mole, the rate constant is 0.404. If you consider this Arrhenius equation, we can use the log version of Arrhenius equation to plot a graph. What is Arrhenius equation? K equals AE exponential minus EA over RT. So if we are using ln K equal ln A plus ln E exponential minus EA over RT. So we can rearrange this equation as ln K equals ln A minus EA over RT. Here I am giving the graph ln K versus 1 over T. You can see the gradient equals to minus EA over R. The intercept is equals to ln A. If it is ln A, the gradient should be minus EA over R, but if it is log K, then gradient should be minus EA over 2.3 R. Now we will discuss the effect of catalyst. A catalyst is a substance that increases the rate of reaction without being used up in the reaction. It works by providing an alternative reaction path that requires a lower activation energy. The Maxwell-Boltzmann distribution curve is unchanged in shape, but the position of activation energy is shifted to the left so that a greater proportion of molecules have sufficient energy to react. Heterogeneous catalyst. First, we will see what are heterogeneous catalysts. They are catalysts that are in a different phase or state to the species in the reaction. An example of this is the contact process. Solid vanadium pentoxide is used to speed up the reaction between sulfur dioxide and oxygen gases. The overall reaction, sulfur dioxide and oxygen react, both are in gaseous phase and form sulfur trioxide. It is also in gaseous phase, but we are using catalyst as vanadium pentoxide. It is in solid state. So we can say it is a heterogeneous catalyst. Now we will discuss adsorption. A solid catalyst works adsorbed molecules onto an active site on the surface of the catalyst. These active sites increase the proximity of molecules and weaken the covalent bonds in the molecules so that what happens? Reactions occur more easily. Rate of reaction also increasing. The strength of adsorption depends on the type of catalyst and can reflect how much it affects the rate of reaction. Here I am giving an example, the reaction between ethylene and hydrogen. What is the catalyst we are using? Nickel. Here ethylene and hydrogen both are in gaseous phase. Nickel, or if we can use platinum or palladium, all of them are in solid state. So here it is a heterogeneous catalyst. So what happened? This adsorption process is using. Now we will discuss model questions and answers. Question number 1. Explain what is meant by the following terms. Number 1. Rate of reaction. Rate of reaction means change in concentration of reactants in a given time. Or we can say change in concentration of products in a given time. Next definition, they are asking overall order of a reaction. Sum of the powers to which concentration terms are raised in the overall rate reaction. Question number 2. Explain why the order of reaction cannot be deduced from the stoichiometric equation for a reaction. The rate equation only includes those species involved in the rate determining step, or we can say the slowest step. Next question. Substitution reactions of halogenoalkenes can proceed via SN1 or SN2 mechanisms. When 1-bromobutane, 2-bromobutane, 2-bromo-2-methylpropane. 1-bromobutane is a primary halogenoalkene, 2-bromobutane is a secondary halogenoalkene, 2-bromo-2-methylpropane is a tertiary halogenoalkene, are reacted separately with aqueous sodium hydroxide solutions. Each gives the corresponding alcohol. The question they are asking, give the mechanism for SN1 reaction between 2-bromobutane and hydroxide ions. As we know, SN1 reaction type is going to tertiary halogenoalkanes, but secondary halogenoalkanes like 2-bromobutane also can undergo SN1 reaction type according to the medium. Here what happened? First, carbon and bromine bond is breaking, and the second step, OH minus is going to attach to the carbocation. That's why it is going under SN1 reaction type. Next question they are asking, explain why the product mixture is not optically active. The answer, the reaction goes through a planar intermediate and this can be attacked from either side, producing an equal mixture of two optical isomers. We can give a separate name, racemic mixture, or another name, 50-50 mixture. Next question, in an experiment designed to find the mechanism of the reaction between 2-bromo, 2-methylpropane and hydroxide ions, the following data were obtained at constant temperature. Here they are giving the data table. Use the data to deduce the rate equation for the reaction of 2-bromo 2-methylpropane with sodium hydroxide solution. According to the data they have given, we can see when double the concentration of 2-bromo 2-methylpropane, the rate is also doubling. When triple the concentration of 2-bromo 2-methylpropane and double the concentration of OH minus as well, rate only up 3 times because it is not dependent on concentration of OH minus. Therefore, we can say rate is equal, rate constant, the concentration of bromoalkane. Assignment, you can complete all checkpoint questions and all chapter end questions under topic 11 kinetics. Here I am giving some reference PDF and YouTube links. You can try out. Thank you for listening to my presentation.